Welcome to the last lecture of formal models. Today we will talk about discrete probabilistic systems. In particular, we will talk about Markov decision processes and how they fit into our framework of formal models. And in particular, we will see that there is a close connection to the finite automata as we have introduced them at the very beginning of this course. Markov decision processes play an important role in the modeling of practical systems where we have effects that are of statistical nature, which we can assume that they happen with a certain probability, and hence it is important that we also have a concise notion of such system as well. They are also very important in another context, and this is reinforcement learning, and they are the underlying model in order to apply this very important technique of learning. Here we have the situation that an agent is put into a world and has made decisions. He has some information about rewards which are connected with the action it takes, and the task is to find an optimal solution to achieve a certain goal. And also here we have this statistical effects that have to be considered or statistical properties that have to be considered when actions are taken. And as we will see, these Markov decision processes fit very well into the framework we have used in this lecture and are simply an extension of the finite automata concept that we have seen at the very beginning of this course. Before we start with the introduction of Markov decision processes, however, we will first talk about Markov chains in order to get a understanding about how to introduce probabilities into an automata, and also for understanding what this means. And then we will extend it to Markov decision processes, which gives us this very powerful formalism used in several applications. What is the motivation of doing this? We want to capture random phenomena, and we want to find models for probabilistic systems. This plays an important role in randomized algorithms. So there are situations where we do not implement a program in a deterministic manner, but where some random component is included in the realization of for solving a problem. For example, when there is a group of processes and one process should take the lead, or when a group of processes should come to a decision, then sometimes it is useful to include a random choice as a tiebreaker. Otherwise it could happen that the execution of the program gets stuck, and then some randomized choice can help. And then we also want to understand what is ongoing and to verify the behavior of such an algorithm. This is, for example, when a dice is used to make a decision, and for this purpose we also need to capture this random choice in the formal formalization of the program. When we model real-world systems, then we also want to capture unreliable and unpredictable system behavior. Consider, for example, a system that is built for transferring information between several parties, and then it can happen that from time to time a message gets lost or corrupted, and this should also be included in the model of the system. And this is then important for coming up with solutions to handle such problematic scenarios. In principle, we could capture these problems with dedicated events or actions in the finite automata model, but this might not really reflect reality, because the message loss should not have the same weight as the successful delivery of a message, and therefore it would be nice to have information about the likelihood that something happens, and then use this statistical information for a more detailed analysis and for the problem solving. And this can then be useful to quantify the problematic cases, and then probabilities can help to better understand what's ongoing and react adequately. Another important application for considering probabilistic aspects in models is model-based performance evaluation. Here the aim is to forecast system performance and dependability and use probabilistic information for analyzing, for example, the distribution of the message transmission delay, or for analyzing failure rates of a processor and things like that. This information then helps to evaluate quantitative properties of the system and make statements about waiting time, queue length, time between failures, and similar aspects. So this can also help to better understand what's ongoing. And there are different ways for dealing with randomness and enriching transition systems with probabilities. And in the following, we will consider two ways of doing that. First, we will introduce Markov chains, which are very popular for the evaluation of performance and dependability in information processing systems. And after that, we will consider Markov decision processes, which, as I said, have applications in very different fields. But before we do so, let's have a quick reminder on some terminology that is used in order to talk about probabilities. So first of all, we have the sample space, big omega, and we now talk about experiments, like for example throwing a dice, and the sample space describes the possible outcomes of an experiment, and an event is a subset of the sample space. And what is interesting, or what we are interested in, is the probability P, which is the likelihood that a certain event occurs. Here I have an example. For example, in our example, we consider tossing a fair coin. This means the sample space is head or tail. Then in this context we have the following events. We have the event head, that the head of the coin is shown, and we have the event tail, that the tail of the coin is shown. And since it is a fair coin, both head and tail have the same probability. As you should remember, the total probability should sum up to 1. So, and 0.5 times 2 is 1. In this case. Then we have, as another example, the toss of 2 fair coins. Then 4 things can happen. We can have 2 times head. We can have head for the first coin and tail for the second coin. We can have tail for the first coin and head for the second coin, and we can have 2 times tail. And an example of an event could be that at least one of the coins shows head. This is a bit of other kind of event, and this means, or what are the interesting cases? This is the first one, the second one, and the third one. And if we assume that both coins are fair, then each of these elements of the sample space happen with a probability of 1/4. And therefore, for the event E, which asks for the probability of having at least one head, we get the value 0.75. Yeah? But here I do not want to go too much into detail. This you should have discussed in other courses. This is just a reminder and introduction of the terminology on probability that we will use in the following. Before we have a look at the formal definitions of Markov chains, let's have a look at the following example. Assume we want to have a dice which is fair and which has 6 sides, as the standard dice has. The problem is that we do not have a device for tossing the dice, but we have only a fair coin, so the coin has 2 sides. And the question is, how can we simulate the behavior of a fair dice with a fair coin? And in the following I will show you an algorithm that was proposed by Knuf and Yao, and it deals with the problems we have when simulating the dice with the coin. On the one hand, we have only 2 sides on the coin, so we have to come up with a way such that the value of the dice is decided by multiple by tossing the coin multiple times. And this is one problem. And the other problem is that if we toss, for example, the coin 4 times, we get 8 possible outcomes, and therefore we cannot easily map them to the sides of the dice, as then one side or 2 sides would have a stronger probability, or we would have invalid outcomes. And in order to deal with these issues, Knuf and Yao suggest to do the following. We start in state. This is here now shown with the following diagram. So we start in state S0, and we have outgoing edges. One represents head and one represents tail. Say left is head, right is tail. Here This is a bit unfortunate. Here we do not see what is left and right. Say up is head, and we do not see what is head and tail, not what is left and right. So up is head and down is tail. But it doesn't matter if you change it. Okay, and what is now happening? If we're in state S0, we haven't tossed the coin. And if we toss it once, then we split the dice. If we get head, then this means we are now choosing among 1, 2, 3. If we get tail, we are choosing among 4, 5, 6. Then we toss the coin again. Let's continue on the left side with the state where we could have a 1, 2, or a 3. If we get a tail, then say we are in a state where 2 and 3 are left for choices, and if we toss the coin again, then we decide then this decides if we take 2 or 3. Yeah, now here in the state 1, 2, 3, we have now discussed the right branch, but what is in the left branch? The left branch, if we put 1 here, then 1 would have more weight than 2 and 3. This is we do not want to have, but what we do is the following. We introduce a state where we again choose among 1, 2, and 3. If in the one case we and again, if we toss the coin, then in the one case we assume that 1 is now selected, and this is then a final decision. In the other case, this leads us back to state 1, 2, 3, and we make a fresh choice between these 3 outcomes or sides of the dice. Yeah, and in effect, if we take the overall probability that we get 1, 2, or 3, so that we get 1, or that we get 2, or that we get 3, then we see, okay, if we follow the paths, this is in all cases the same. Yeah, and this is because of the trick here that we also distinguish between 2 cases. One case is once is selected, and the other case is that it's not selected, and then we restart here in the selection of 1, 2, and 3. The same we do here on the right hand. On the right hand side of this graph, and down here in the leaf nodes we have the final results, so when some selection has been made, and these are states where we stay forever, no matter how we toss the coin. Important is that we did not annotate the edges with labels, so we did not indicate that we have the event head or tail, but we say with a probability of 0.5 we go there, and with a probability of 0.5 we go to the other side. Yeah? So this is an important property of Markov chains, that we do not have any actions but just the probabilities of the state transitions, and this makes the model very easy to specify. And now we can say a Markov chain M consists of 3 parts. So we have a triple that contains a set of states. Then we have an initial distribution, which is a function that maps the states to values between 0 and 1. 0 and 1 is also included, in such a way that the sum of all the values we get from this initial distribution for all the states is equal to 1. Yeah? And if we have a state that has if we have a state IS with 1, then this means that we have only one initial state. If we have a state where IS is 0, then this means it's not an initial state. Okay, but in principle we can have multiple initial states, and we know that the distribution and gives us the probability with which we start in a certain state. And then we have the transition probability function, which maps two states to a value between 0 and 1, such that for all states S, it holds that the sum of all transitions that can made from this state to any other state, such that this probability is in total 1. Yeah? And let's have a look at our example. So here we have the states. We have the states in the oval boxes and in the squares. The squares I just used in order to indicate that we cannot really proceed from these states. And if we look at the edges, which represent this transition probability function, then we see that it is indeed the case that the numbers given on the outgoing edges of a state sum up to 1. 0.5 plus 0.5, for example, we have here gives 1, and this we have for all states. 0.5 comes from the property of the coin of being fair, and here with probability 1 we stay in this state. Yeah, and again we do not have any actions and only this probability distribution. And in this example we have one initial state S0, and therefore I of S0 is 1, and for the other state it's 0. Yeah, and this is actually what we this is the kind of information we have in a Markov chain. And note that we can alternatively represent a Markov chain as a vector, and there we have the information that gives us the initial distribution in this vector. So we have state S0, S1, S2, S3, and so on. We have to know the mapping, and we know which value with which probability each state is an initial state. And we also can write it down as a matrix where we have the states times states, and each entry gives us the probability to move from one state to another state. And if it's 0, we cannot go. If it's 1, we go for sure, and there is no choice. Yeah, and so when we look at these Markov chains, what do we have? We have in principle a state transition system that does not include any Boolean variables or for characterizing the states. It also does not include any actions, but what we have is we have the probabilities that indicate how or when or with what likelihood transition from one state to another is performed. The Markov chains do not have any memory about previous decisions, so this is also something what we did not have in the finite automata. We did not look at the past in order to decide how to proceed next, and therefore the future states are independent of the past states. Then every state has at least one outgoing transition, and those states S prime with P as S prime larger than 0 are possible successors of S. Yeah, if it's 0, then this means there is no transition. Then for the initial state, we require that IS, for initial states S, we require that IS is larger than 0. These are the possible initial states. And then we have some special states which are called absorbing states, which have a self-loop, and the probability for going from S to S is 1, and in consequence for all other states different than S is 0. And in our example here, the 6 states here at the bottom are absorbing states, so here we do not proceed and stay there forever. Yeah, and we can also write down the probability that we move to a certain subset of states, and this is simply the sum of the probabilities of the states in this subset. Yeah, and this is in principle these are the most important or interesting or for us at the moment most interesting properties of Markov chains. There is much more, and yeah, I want to keep it with this. I will not go much further into details. The point that I would like to make here is that this is a simple or a variant of a finite automaton as we have seen them before. Now we have probabilities included and can therefore deal with a probabilistic aspects in the execution of a system. Yeah? And for such representations of a system, it's also possible to perform verification tasks. Also here, temporal logics could be specified. Then, somehow properties of the states have to be included, and then also model checking can be performed. But then in this context, the probabilities have to be taken into account. Yeah? But this I just wanted to point out. We will not do this in this course. Now let's compare labeled transition systems and Markov chains. So we said that labeled transition systems are defined as follows. We have the states, we have initial states, which are a subset of the states. Then we have an alphabet modeling the actions that are possible, and we have a transition relation that tells us how we come from one state with a certain action to another state. And with this we are able to model non-deterministic behavior in the sense that if we are in a state, then several kinds of events or actions can happen, and we then continue in the respective target states. Yeah, so for example, if we are considering this system where we want to exchange information, then if we're in the send process, and then it could happen that everything works and we are in the received state, or it can happen that there is a message loss, and we end up in an error state. And in this case, or in such a scenario, we would have two outgoing edges, and one models the error situation and one models the standard case. Yeah, and here we cannot say which of the two situations is most likely. We only say that either the one or the other happens in this state. In a Markov chain, on the other hand, we also have states, but we have distributions to indicate, on the one hand, what are the initial states, and we also have this probability function that tells us with which probability we come from one state to a certain other state. And with this, we are now able to model probabilistic behavior, and we can say that, for example, message loss is only happening with a probability of, or with a very small probability, and that the standard case is that everything is fine. Yeah, and this we cannot express with LTS. On the other hand, we do not have any actions in the LTS, so we cannot say that this action is taken or this action. And in many cases, we want to combine it. We want to have probabilistic behavior, and we also want to have the actions in order to have a choice and telling what is exactly the next event or the next action. And for this purpose, Markov decision processes have been introduced, and we will see how they combine concepts of both elements. So what we want to have is we want to have probabilistic and non-deterministic choices in one model. We want to have it for modeling randomized and distributed algorithms and for quantifying the outcomes of randomized actions. This is one motivation to have it. Yeah? So this is in particular important in the context of verification, where we want to make statements about the system properties. And we also maybe want to perform model checking on such models. On the other hand, Markov decision processes are also used in a very different context, and they are used to formalize an agent environment interaction scenario. Yeah, so we have an agent or multiple agents that interact with their environment, and this they do with the intention to reach some goal state. And in order to reach the goal, the agent has to make certain decisions, and the decisions can, as in real life, be good or not so good. They can be more target-oriented or not so target-oriented. And the aim is now to produce an optimal behavior that balances risks and rewards. I mean, it can also happen that decisions are totally wrong and that they maybe do not lead towards the goal, or maybe that they even do harm to the agent. For example, if it's a robot and a robot that is exploring the world, and if there is a hole and the robot falls into it, then this was definitely the wrong decision if it gets damaged by that. And yeah, this is necessary to have a formal model for acting in an uncertain environment. And in learning-based scenarios, the application of Markov decision processes is in the context of reinforcement learning. Okay, so now let's have a look. What is a Markov decision process and what are its components? We have now a set S of states. Then we have the initial distribution as before, which maps each state to a probability such that the total amount is 1. So the sum of the initial distribution over all states is 1. Yeah, this is as before. Then we have a transition probability function, and now this includes also actions. So we do not have only two states, a target state and a source state, but we also have an action included. And this triple state, source state, action, target state is mapped to a probability, and this is done in such a way such that for all states and all actions, the sum of all target states is either 0 or 1. Yeah, meaning that in a state an action can be done or it cannot be done. And if it can be done, then it's not done with a probability of 0.5 0.5, but it is done with a probability of 1. It's just not clear what is the target state. In addition, we also have a reward function, which gives us information about the gain or the loss when performing a certain action in a state. So this reward function can also be negative. And there is a discount factor, which we will discuss a bit in the end of this lecture. Okay, and here I have a collection of some properties of Markov decision processes. We call an action A enabled in a state S if there are target states that are reachable when executing the action, and we require that every state has at least one enabled action. And if each state of the Markov decision process has exactly one enabled action in each state, then it's equivalent to Markov chain. And now some intuition about how a Markov decision process can be understood. A starting state S0 is entered according to the initial distribution by a stochastic experiment. So for example, we could throw a dice and say we start at this initial state. Then when an enabled action A is selected, then the successor state is randomly selected according to the distribution of the action in this state. Yeah, so we have on the one hand this non-deterministic behavior that an action can be selected at the state such that this action is executed, and if we have selected an action, then we use the probability distribution in order to decide where to go next, and then this next state is entered. Yeah, and again, if we want to talk about the probability that one of a subset of states is reached by an action A, then this is simply the sum of those target state candidates. So this is very similar as before. Here we have an example of a Markov decision process. I chose an abstract, simpler example than the example we had for the coins and the dices before, because we can discuss it also here with the smaller abstract example. We have 4 states, S0, S1, S2 and S3. We have exactly one initial state because I of S0 is 1. So S0 is the initial state and there are not multiple ones. Then we have the alphabet ABC. And now let's see what is happening. In state S0, action A is enabled, and there we have the following probabilities. With a probability of 0.8, with a very high probability remain in state S0 when executing A. With a probability of 0.1, we go to S1 when executing A, and with a probability of 0.1, we go to S2. Then for the other states, we also have some actions that are executed, but those are executed with a probability 1. So here in S0, S1, we can choose to execute action B or A. And if we execute action B, then we go to state S3. If we execute action A, we go to S2. In S2, we can execute action C only, and then we go to state S3. And in state S3, there is only one action that is executable, and this is state A, action A. Here on the last bullet, I have described how this transition probability function looks like, but the information should be equivalent to the information found here in the graph. Yeah. Okay, what we did not include here in these examples are rewards. Let's maybe quickly talk about rewards, what they are good for. When we have this agent-based scenario, then the agent does not necessarily know, or often does not know, what action is a good choice, what is a bad choice, and it has to learn what it should do. And in order to do so, the reward gives some indication what is a good choice and what is a bad choice, and what now has to be solved is an optimization problem that maximizes the cumulative reward in the long run. And for this purpose, we introduce the notion of expected return. If we have rewards that are obtained after time step t, so we have reward rt plus 1, rt plus 2, and so on, then the expected return at time point t is the sum of all the future rewards. So we simply sum up the rewards in order to obtain the expected return. This can be a finite sequence if we have tasks that will finish at some point. For example, if we are playing a game like tic-tac-toe, then we know after a certain amount of moves we are done and cannot proceed anymore. It can also be infinite for continuous tasks, for tasks that do not terminate. For example, when we have the model of a robot, then we might not want to include the end of the robot, but we want to assume in our model that it has an infinite life, and then this sum is not finite, but it's infinite. Okay, and here in our example, I've now added some rewards for the actions we have here, and what is important is that we do not have only positive rewards but also negative rewards, which are basically some kind of penalty that is given if something is done wrong. Yeah, so this is the reward function. What we also had in the definition of the Markov decision processes were discounts, this gamma, and this is important when we want to realize a more far-sighted agent, because a reward might be more valuable now than in the future, and this can be because of inflation or obliteration, and therefore this discount reduces the value of a reward that we obtain when performing a certain action. And this is written down here. I also do not want to discuss this in detail. The important thing is only that the discount is a factor with which the reward is multiplied, and this means the closer the discount is to 1, the less impact it has on the value of the rewards. Yeah, but again, I don't want to discuss the details here because we do not have discussed, or we don't. For us, it's not important at the moment to discuss how to calculate this GT. I just would like to point out that it is often that the rewards and the discount are part of the definition of the Markov decision processes. It's also important that in the literature there are several variants how to define MDPs, and you have to look it up how it is exactly defined in the literature or in the book or in the article that you are reading, and what is included and what is exactly the purpose. So there are different ways of writing it down. The way I presented it was in such a way that it fits into our framework of finite automata that we had consistently through the whole course, and that it becomes mainly an extension of concepts and languages we have already seen before. Yeah, and to conclude, I would like to point out that the aim is to calculate certain policies when used in the context of modeling an agent with interaction with its environment. And what is a policy? If we have an agent, then this agent wants to achieve a goal, and the important question is, what is the solution to achieve the goal? What is a good solution? In the context of MDPs, it's not enough to find just one plan, to find a fixed sequence of actions, as we had it in the planning problem. This is here not enough, because we want to have an agent that can react and take actions in every state. So in every state that the agent encounters, it knows how to proceed. And therefore a policy is a solution that specifies what an agent should do in any state that it reaches. Yeah? So we have to consider an action for every reachable state. And if such a policy is complete, then the agent always knows how to react and what to do next. And we call a policy optimal. That is the thing that, or the policy that we want to find. Then the policy always yields the highest expected utility. So the agent performs always optimal. And as I already mentioned, this is the basis for reinforcement learning, and therefore a very important model that has a lot of very successful application nowadays. With this pointer to reinforcement learning, I would like to conclude this lecture, and thank you very much for watching and your attention. Goodbye.